Okay guys, this video is all about the separation vector. That's what we call the R vector, or the script R vector, which is the vector connecting the source charge and the test charge. For reading, again, we're still kind of cruising along the first couple of sections of chapter 2. Chapter 1 in the book is all about math, right? Some advanced math you're going to use in this class. So we're going to skip back there as we need to. And 1.1.4 is a chapter that might be useful for you to review. It's about position vectors and some of the vector addition and subtraction that you guys have learned but maybe haven't done in a while. Okay, so in this particular video, I'm going to describe how the separation vector relates to the position vector of charges in a coordinate system. All right, so let's go ahead and start with a picture. Okay, so same picture I've been drawn every single lecture so far, I think. Q, little q, okay? That is our source charge. Big Q over here is our test charge, okay? Now, let me see here. I'll draw this, okay? This guy right here, which is not the straightest line I've ever drawn, okay, vector R, this is what is known as the separation vector. That's what the book calls the separation vector. It is the vector that separates our two charges, okay? So let's figure out how we can actually figure out what this separation vector is in a particular coordinate system, okay? Or I like to think of this lecture as, why the heck did they use this cursive R? People don't even learn how to write cursive anymore, I don't think, rather than the regular R. Okay, well the reason for that is that when we're solving E&M problems, okay, using Coulomb's law or anything else, actually I'm going to put this a little bit differently, make my life easier. Okay, I'm going to want to define a coordinate system. Okay, I'm going to want to define a coordinate system so that I can figure out where these charges, what the position is in this particular coordinate system. So the way that we do that, if you guys recall, is we define position vectors. Okay, so position vectors, you guys remember hopefully that. If not, that's okay. We're going to define it right now. A position vector is a vector that goes from the origin, points from the origin to the object, in this case a charged object, okay? So I've drawn one position vector here. This is the position vector for the source charge, and R, regular R, is what we've always used for position vectors. So that's why we got to use script R for the separation vector. Regular R was already taken for position vectors. So this is some notation to try to remember and keep track of because the book uses it, okay? It even makes a note when it chooses not to use it. But we're going to use apostrophes or primes, okay, to separate this position vector for the source charge from the position vector of the test charge. Okay, so our R prime vector is the position vector, okay, of our source charge. So try to remember that when you see primes, we're talking about source charges. All right, and this is a really long one to draw straight. Okay, it's straight-ish. My hand kind of gets stuck on the iPad sometimes. Okay, our R vector here with no prime, that's going to be the position vector of our test charge, okay? That's why there's primes and not primes. Both of them are R because they're both position vectors, okay? All right, so if you're looking at this and you can remember vector subtraction, okay, I'll write it right here. A way to calculate what our separation vector would look like if I knew the position vectors of both of the charge objects, which I know if I just know the position of those objects in the coordinate system, okay, would be to use a little bit of vector subtraction. So our separation vector is R r, okay, the position vector of the test charge, minus r prime, okay? And this is good old vector subtraction. Okay, so we should be going back into our brains and remembering how I do vector subtraction graphically, right? How I do it using unit vector notation. Okay, these are the kind of things we're going to be reviewing. So just to remember how you do it graphically, I won't actually do it precisely here, but right, we're going to take this vector, okay, our r vector, and we are going to subtract our r prime vector. What that means is, if you guys remember, we're going to add the negative of our r prime vector. So the negative of the r prime vector added to the r vector, that's going to look something. I'm going to just draw it temporarily here like that. Okay, so remember where that vector is. And if I were to draw the resulting addition of those two vectors, it would look something like that. Okay, which is approximately, right, just kind of eyeballing it, the same as our separation vector. Okay, so our separation vector is a result of vector subtraction of the position vectors of our source charge and our test charge. All right, so that's the separation vector. Let's talk about our unit vector r hat. Okay, so how do you figure out our script r hat? Okay, so this is our unit vector that's in the same direction as our separation vector. Okay, so the direction, if you remember, the direction is the same as our r vector, but the magnitude, that is not how you spell magnitude, the magnitude is 1, okay? So how do you do this? Well, you can, if I think about it, I can divide, if I divide the vector r hat by its magnitude, I'm just left with a vector that has the same direction as r, but has a magnitude of 1. So that is a crazy R script. Let me try that again. That's what we're going to do. So r hat is going to be equal to our separation vector divided by the magnitude or the length of that separation vector. Okay, that's going to take our separation vector, no matter what it is, okay, and it's going to shrink it down to our unit vector that has a length of 1. Okay, so mathematically that's what it looks like. Let's just do that in Cartesian coordinates. So I'm going to draw another quick little picture over here. Make that a little bit bigger. Got a coordinate system, just 2 dimensions for now. Well, I'll throw a 3rd dimension in there actually, just kidding. 3 dimensions, okay. This is a right-handed coordinate system. How do you know it's right hand? Well, if you cross the x-axis into the y-axis, your thumb is going to point into the z-axis. So hopefully you guys can see me. If you can't see me in the video, if you're not looking at the video, I'm trying to do that cross product with my hand. Okay, I'm going to draw a couple of charges here again. Q, little q, big Q, okay. Yeah, that's terrible. There is our r prime. Okay. There is our r. Okay, if I was going to write out the actual coordinates of these particular, or the positions of these particular charges in this coordinate system, I would continue with that same notation. So I can also, instead of defining the unit vector or the position vector to give the position of these 2 charges, I could just give their x, y, and z locations. For the test, or for the source charge, I'm just going to put primes on the x, y, z to indicate that those particular variables are related to the source charge. Okay, for our test charge, no primes. Okay. So in this coordinate system, right, our R vector or a position vector could be also described by our x, y, z coordinates. Okay. Nope, that is not a z. Talking and writing. Okay. If I wanted to, using our coordinates, figure out what my separation vector is going to be, right? I'm going to take my position vector for my test charge minus my position vector for my source charge, okay? And if I know what the actual XYZ positions are, it's as simple as this, okay? All right, that's not too bad, right? Okay, so if I know my positions in a coordinate system of these two charges and I want to figure out what my r hat vector is going to be, that unit vector, okay, remember I'm taking my script r over the magnitude of the script r, that's the separation vector. Okay, to be super explicit, that's the same thing as doing the subtraction of those two position vectors over the magnitude of the results of the subtraction of those two position vectors. Okay, so that's basically the magnitude of our R vector, our separation vector. Okay, math-wise, again, not too bad. We're still getting a vector here out of it. Okay, so this top part, because it's got three components, it is giving me the vector's direction in our three-dimensional coordinate system. And I'm going to divide it by the magnitude of that vector. That is going to be its components in the x, y, and z direction squared, and then the square root of that, okay? I'm running out of space here. Okay, that is a squared. Okay, so if you know the coordinates of, or the positions of the source charge and the test charge in a Cartesian coordinate system, it's really no big deal to calculate what each of these vectors are, okay? And again, if I were to, I'm just going to simplify this a little bit, just for right now. This is not like some kind of standard notation, but let's just call this, now I'm just going to pick a variable alpha. Okay, if I were going to write r hat, again, this is just super review. I'm trying to be really explicit here. If I were going to rewrite r hat in a different type of notation, our unit vector notation, it would be equal to x minus x prime over this alpha thing, this variable I just made up so I didn't have to write out that big thing in the denominator. Okay, that would be the length of the vector in the x hat direction. So our unit vector pointing in the direction of the x-axis. If you guys remember, okay, the standard notation for that unit vector is I hat, okay, and that would be the standard notation describing the vector's length in the y direction or the j hat direction. Okay, and then if we have a three-dimensional problem, sorry, I'm running out of space here, alpha k hat is our unit vector that points in the direction of the z-axis. Okay, so this is just to get really explicit that this type of notation here, when you've got these parentheses, you're really just giving the components of the vector, the length of the vector in these three directions in your coordinate system. Okay, so again, if you guys need to review a little bit of this vector addition and subtraction, position vectors, go back and read 1.1.4 in the book, or if you really need to, you can crack open that night book from your first year of physics and read about them right at the beginning there. Okay.